Not having enough data to train your machine learning model is a very common problem in the field of computer vision. However, it is also a problem that we can solve pretty easily using image augmentation. Hi, and welcome back to our channel. I'm Boris Delovsky from Edlitra, and I'm very excited to bring you the first part of our two-part series on using the Albumentations Library in Python to perform image augmentation. In this video, we'll cover the basics of computer vision, image augmentation, and also pixel-level transformations. By the end of this video, you'll have a solid understanding of what image augmentation is and how you can use the Albumentations Library to perform various pixel-level transformations. In the following video, we will cover spatial-level transformations and building image augmentation pipelines. As always, we strive to bring you high-quality educational content, and we appreciate your support and feedback as we continue to grow our channel. So, if you found this video helpful, make sure to hit that like button and subscribe to our channel. And now, without further ado, let's get started. As we prepare to delve into the truly fascinating realm of image augmentation, it's essential to first lay the foundation by discussing computer vision in general. Computer vision is an interdisciplinary domain encompassing various techniques that empower computers to extract valuable insights from an assortment of visual inputs, namely images and videos. Interestingly, videos are nothing more than a sequence of images. In other words, a video is a compilation of images presented in rapid succession. This creates the illusion of motion. Now, this crucial fact implies that any technique applied to an image can also be applied to videos by implementing it on each individual image within the video sequence. So, how do computer vision systems actually operate? Well, it's intriguing to note that they function in a manner strikingly similar to human vision. Our eyes perceive images and relay that information to our brains, which then process the information and generate data. Computer vision systems adopt a similar approach, using sensors such as cameras instead of eyes. These cameras capture images, convert the images into digital signals, and then transmit those digital signals to a computer. The computer will then take those digital signals and process them, ultimately transforming them into data. Now, let's address the question of what are exactly images. Well, fundamentally, images are comprised of pixel data. To a computer, an image is essentially an array of numbers, each number representing one pixel. The numerical representation of a pixel depends on whether the image is in color or grayscale. In the case of grayscale images, each pixel is assigned a numerical value within the range of 0 to 255. 0 signifies black and 255 denotes white. All of the intermediary values here represent varying shades of gray. By representing each pixel with a numerical value, we can create a matrix of these pixel values. This matrix gets passed to the computer processes this matrix, and that's how it extracts meaningful data. On the other hand, in the digital realm, color images are created using a combination of three primary colors: red, green, and blue. These colors facilitate the representation and display of intricate images on screens and devices. To comprehend how color images are formed and processed, we must first delve into the concept of color channels. A color channel is an image component that contains intensity values for a specific color. In color images, we usually encounter three channels: one for red, one for green, and one for blue. Each channel is essentially a grayscale image with values moving from 0 to 255. But in this case, 0 still represents the lower intensity, but 255 signifies the highest intensity or the full color. For example, if we allocate a value of 255 to the red channel and 0 to the green and blue channels, the resulting pixel will be entirely red. In contrast, setting the red channel to 255, the green channel to 215, and the blue channel to 0 will produce the color gold. So as you can see, understanding the basic principles of computer vision, images, and color channels is essential before we delve into the more advanced topics such as image augmentation. Image augmentation is a powerful technique centered around generating novel synthetic images using existing ones, primarily aimed at enlarging the dataset that we are working with. The significance of this process is rooted in the fact that computer vision models thrive when presented with copious amounts of data. The larger the dataset, the better our results will be. In many situations, we may find ourselves lacking the necessary volume of images to train our model. This obstacle can be surmounted by enhancing our dataset with the creation of these so-called fake or artificial images. How do we create fake images? Well, we manipulate pixel data. Manipulating pixel data can be broadly classified into two distinct categories of transformations: pixel-level transformations and spatial-level transformations. Pixel-level transformations involve direct modification of individual pixel values. For instance, we can take a pixel with a value of 246 and adjust that value to 216 or a similar value. Conversely, spatial-level transformations concern the relocation of pixel values within the image. For example, we can take the top left pixel and move it a few spaces to the right. While these altered images might seem virtually indistinguishable or even even identical to the human eye, computers perceive them as entirely distinct due to their numerical matrix representation. Any changes or modifications to the matrices that represent images will result in the computer recognizing the new image as a unique image, even though the difference between it and the original image is negligible. Numerous Python libraries exist for image augmentation purposes, but the most notable among them is the Albumentations Library. It was specifically designed for image augmentation. It's not intended for generic computer vision tasks. It empowers users to seamlessly perform both pixel-level and spatial-level transformations. It has a very user-friendly interface and is optimized to be effectively employed for a broad spectrum of computer vision tasks. Its versatility and adaptability render it the most popular choice among developers working on diverse computer vision projects. By harnessing the capabilities of the Albumentations library, any user can expand their dataset, which will in turn enhance the accuracy of their models. Let's talk about pixel-level transformations and spatial-level transformations in detail. Let's talk about pixel-level transformations first. Pixel-level transformations are widely employed due to their relative simplicity compared to spatial-level transformations. Remember, spatial-level transformations are transformations where we change the positions of the pixels themselves, which can bring about many problems if you're working on a task such as object detection or other more complex computer vision tasks. On the other hand, pixel-level transformations are transformations where we change the value of the pixels themselves. For example, we take a pixel that has a value 200 and change it to 157 or perform any similar adjustment. This makes these transformations very effective and also easy to use, making them a very popular choice in the world of image augmentation. Among the most prevalent pixel-level augmentations or transformations are image sharpening, image blurring, histogram equalization, noise addition, and color manipulation. Each of these serves a unique purpose in enhancing and diversifying your dataset, so let's talk about each one of them separately. First off, image sharpening. By accentuating the differences between a pixel and its neighbors, this technique amplifies the edges and details on an image. For example, if a pixel has a value of 200 and its surrounding pixels have values of 180, sharpening might increase the value of our pixel from 200 to 220, thereby enhancing the contrast between the pixel and its neighbors. On the other hand, we have image blurring, which is the exact opposite. This method works by averaging the pixel values with those of their neighbors. So if we started with a pixel that has a value of 200 and its neighboring pixels have values of 180, blurring might reduce the central pixel value to 190, resulting in a smoother, less detailed image. After image sharpening and image blurring, we also need to talk about histogram equalization. Histogram equalization is a technique that redistributes pixel intensity values to achieve a uniform distribution. Suppose an image has a majority of pixel values between 100 and 150, which typically leads to poor contrast. Histogram equalization might try to spread those pixel values more evenly across the range between 0 and 255, which should in theory improve the overall contrast of the image. Aside from histogram equalization and the aforementioned two methods, we also have noise addition. Introducing noise involves randomly modifying pixel values by a very small amount. So if a pixel has a value of 200, we might change it to 205 or 195, depending on the noise level and distribution. This simulates real-world imperfections and helps models become more resilient to variations in image quality. And finally, we have color manipulation. Adjusting color properties typically involves altering the pixel values in each color channel separately. So the red color channel, the green color channel, and the blue color channel. For example, increasing the brightness might involve adding a constant value to each pixel in every channel, while modifying the hue would probably entail shifting the pixel values in a cyclic manner across the color channels. So as you can see, there are many pixel-level transformations that we can use to improve the quality of our dataset, to add artificial fake images to our data. Okay, so at this point, you should have a general understanding of how image augmentation works. Let's actually demonstrate how you can implement image augmentation in Python. First off, I'm going to import three libraries: the Albumentations Library, the PIL library, and the NumPy library. The Albumentations library is the library that I'm going to use for performing image augmentation. The PIL library is a standard Python image processing library. It's important because we're going to use the image module from that library to load in our images and also to convert arrays into images. And finally, we have the NumPy library. It's a numerical library in Python that will allow us to convert our image into an array. Now, why is this important? Well, the general workflow here is the following. We take an image, we load it in, we convert that image into an array, we pass it to our transformation from the Albumentations library, and then we convert it back from an array into an image. So that's how these things generally work. So first off, I'm going to load in the golf ball image. To load in the golf ball image, it can be any image. In my case, it's the golf ball image because I'm using that image for the purposes of demonstration. We can use the open function of the image module. This will allow me to open up my image. image, to load in my image. So at this point, I have this particular image stored in the golf ball image variable. Now, before I can feed this image into the transformation from the Albumentations library, I actually need to convert it into an array, because that library expects arrays as inputs. So how am I going to do that? Well, I'm going to use the array function from the NumPy library. The array function will allow me to reference my image, and it will just convert it into an array of numbers. So after I perform this transformation, my golf ball array variable is going to contain the following array. So this array right here represents my image. Remember, because we are working with images that are in color, we have 3 values for each pixel: red, green, and blue, right? So we will define each pixel with these 3 color values. Now, this is basically my array, the array that I'm currently working with. If I want to perform an augmentation, if I want to transform that array, I just need to define the transformation itself, and then I need to perform the transformation. So when I'm defining the transformation, I will access a particular transformation from the Albumentations library. Now, in this case, I'm using the ISONoise Transformation. This is a transformation that adds random noise to the image, emulating the grainy appearance that you can often see in low light photography. You can use any transformation you want. You just need to check the Albumentations documentation and pick one. Of course, I'm going to demonstrate here the most common pixel level transformations that I've talked about. And I'm going to start with this particular transformation. Now, you might notice this argument right here. So the P argument is important because it tells Python whether I want to transform my image always or only sometimes. Ignore this for now. We're going to talk more about this once we get to image augmentation pipelines. So I'm defining the transformation itself. And after I define the transformation, I can go ahead and apply it to my array. Now, to apply the transformation to an array, I just need to reference the array, and that's it. So I have my transformation that's stored inside of the transformation variable, right? And then I just need to tell that transformation where is my image. And my image is in the golf ball array variable stored in the form of an array. And that's basically it. So if you check what's currently stored inside of the augmentation variable, you will see the following result. Now, what we have here is a dictionary, not an image. So you might be wondering what's actually happening here. The reason why we get a dictionary back is because sometimes when you're working on more complex tasks, such as, for example, object detection, you need a dictionary as a result, because aside from an image, you also need, let's say, the bounding box coordinates or something similar. Now, in this case, we are just transforming the images, so you don't need to worry about this. To get to this array, we're going to access this array the same way we would access anything from a dictionary. So I just need to access the particular value associated to the image key, and I'm going to get my augmented image array. So if I actually demonstrate how this array looks like, you're going to see that it's basically the same array that you can see right here, right? So this is my new array. Now, if I display the image from that array using the fromArray function from the image module, I'm going to get the following result. Now, when you take a look at this particular image, when any human takes a look at this image, we don't really recognize the difference between this image and the original one. However, if you take a look at the arrays, it's pretty easy to notice a difference. Here we have 47, 96, 0, but in the original array, we had 30, 67, 0. So you can see the original array has changed. So even though we humans can't see the difference, computers can actually tell the difference. So a computer will treat this image as a completely new image. This allows us to increase the size of our dataset and will in turn allow us to create models that are more accurate. So to summarize how everything works, we will take an image, load it, convert it into an array, and then transform it using the Albumentations library. Finally, when we transform the image, we get back a transformed array, and then we can convert that array back into an image. And that's more or less it. Now, because I'm going to demonstrate a few other transformations, I'm actually going to create a function. This function, this augment image function right here, takes in 2 parameters. So we have the augment parameter and the image parameter. The augment parameter is the particular augmentation, the particular transformation that I want to perform. There's a lot of different transformations in Albumentations. I'm going to perform those that I mentioned earlier as the most common pixel level transformations. And of course, I also have the image parameter. This image parameter is essentially an image object from PIL that represents the input image. Finally, what we're going to get back is a PIL image object representing the augmented image. In terms of code, this code right here that performs all of these processes is the same code that we had right here. The only difference is that it's all in one place. It's inside of a function. So what this code does is it takes the image that we give to the function. It converts that image into an array using the array function from the NumPy library. It stores the array inside of the image array variable, and then it performs the augmentation. It transforms the image using the Albumentations transformation. This variable right here represents the transformation itself. We give the image array to that particular transformation, and then we access what is connected to the image key in the dictionary. That's the end result. This will give us the augmented image array, and then using the fromArray function from image, we can actually get the augmented image itself. So let's demonstrate how this works on a few different transformations. First off, we said that one of the most important pixel-level transformations was the Sharpen transformation. Sharpen is a transformation that enhances the edges and details in images. To perform the Sharpen transformation, I'm just going to access the Sharpen transformation from the Albumentations library, and I'm going to use the augment image function. What do I need to enter? Well, the first argument that I'm going to enter is going to be the transformation itself. So in my case, the Sharpen transformation. And then I need to input the image that I want to actually perform the transformation on. In my case, it's going to be the golf ball image. So when I run this code, I'm going to get the following result. Now, in this case, you might notice some difference between this particular image and our original image. So as you can see, in some cases, even we humans can actually tell the difference. In some cases, we can't. Now, the other very important pixel level transformation that we talked about was blurring. The Gaussian blur transformation applies a Gaussian blur to the input image, which will smooth the images by reducing high-frequency noise and details. The way this is achieved is actually by convolving the image with a Gaussian kernel, which results in a weighted average of each pixel's neighboring pixel. So essentially, we're going to make sure that every pixel is similar in its value to its neighboring pixels. Again, I just defined the transformation itself. I input it as the first argument, and I input as the second argument the particular image that I want to apply the transformation on. So in my case, I'm going to apply it on my golf ball image, and I'm going to get this result right here. Again, in some cases, even we humans can notice the difference. Then we have the Grayscale Transformation. Now, this was not necessarily mentioned among the pixel level transformations, but I still think it's important. Essentially, in this case, we are working with color images. However, if you want to, you can convert an image to a grayscale image. To convert an image to grayscale, I'm going to use toGray from the Albumentations library, and I'm going to store that as my transformation, my Grayscale Transformation. And then again, I just augment the image itself. I apply the transformation on my golf ball image, and if I store this inside of a variable, Grayscale golf ball image variable, I can then access this grayscale image. That's going to look like this. And finally, we have the CLAHE transformation, which stands for Contrast Limited Adaptive Histogram Equalization. Again, we mentioned earlier that this is a very important pixel level transformation. It's an advanced technique that's used to improve the contrast of an image by redistributing the lightness values across the histogram. Now, unlike traditional histogram equalization, which applies a global transformation to the entire image, this particular type of histogram equalization works on small non-overlapping regions that we typically call tiles and takes into account the local context, which will result in a better preservation of details and reduced noise amplification. Now, basically what happens here is the same as everywhere else. So we take the transformation, we define it, we input it as the first argument to our function, we input the image as the second argument. In this case, I'm going to apply it on the grayscale image, and I'm going to get the following result. So this is my grayscale image with the contrast limited adaptive histogram equalization applied on it. In this case, even we humans can tell the difference. So to summarize, pixel level transformations are very important. They change the values of the pixels themselves. However, we don't change the positions of the pixels. So as you can see, even though in some cases we blurred the image or sharpened the image or converted the image to grayscale or even applied this contrast limited adaptive histogram equalization, the golf ball stays at the same place in the image, right? It doesn't change its position. The only thing that changes are the values that represent that golf ball image when we convert the image into an array. And that's more or less it when it comes to the basics of computer vision, image augmentation, and pixel level transformations. I hope you found this video informative and useful as you begin to explore image augmentation in your own computer vision projects. Don't forget to hit that like button and subscribe to our channel for more high-quality educational content, including the second video in this series, where I'll cover spatial transformations and building image augmentation pipelines. See you next time.